So the talk here is RAID. RAID is an acronym. It stands for Rootkit Analysis, Identification, and Elimination. And I am Peter Silberman, an undergraduate college student on the East Coast. I do independent security research. I co-authored FU2 and also authored the PyMe diff, which is soon to be released. And I contribute to OpenRC, so if you have a chance, check out the site.
And my name's Jamie Butler. I wrote the Rootkit Subverting the Windows Kernel book that was released last year from Madison Wesley, and did the FU Rootkit and contributor there at rootkit.com. Currently unemployed.
Currently unemployed.
So there's the email address.
Email is there. He does not have a business card.
Actively looking for work.
He does not have a business card. Do not ask him. We put the email address in there for you guys. So if you want to get hold of him, there it is. That slide will not be on the internet. So write it down. I'll give you a second, and we're going to move on because we don't want him getting spammed more than he already does. We all good? All right. All right, so what are we going to cover here real quick? We're going to try to do as fast a review as possible. For those of you who were at the R squared, the rootkit, history of rootkits or whatever, they covered some of it. We're going to go a little more in depth. We're going to try to go quickly so we can get through to more interesting stuff. We're going to cover your userland hooks, your kernel hooks, your ERP hooks, your IDT hooks, your model-specific registers. We'll talk about process hiding. Both of us are pretty good at it. We both have written a version of FU. And just for those, just for you, those of you, it's not FU2, it's FU and version 2. So those, just to be specific. And then we'll get into RAID, and we will do a live demo. A lot of people have been showing videos. We are going to do a live demo. Props to Dino for doing a live demo, and you see what happens. So
stick around for the demo.
Yeah, if nothing else, watch the demo.
6 rootkits, 1 VMware, 1 kernel debugger, and our RAID product. We'll see what happens. So many of you already know this. Quick background. What is a rootkit? It has 2 defining characteristics. It's to provide stealth on the system. To do this, usually you have to gain execution control or modify data in the kernel. Another goal of the rootkit is to provide persistence so that you can always come back. A lot of the remote command and control stuff that Alexander will be talking about later in this track deals with that. In order to gain execution control, there's something called IAT hooks. Every executable, like Task Manager and so forth, uses imports from other DLLs, and those imports are patched up at load time, so you can hook into Task Manager or Explorer, any other Windows process, and patch the actual function that gets called on, say, a call to enumerate the files on the file system, or a call to enumerate the open ports, etc. EAT hooks, these are a little more interesting. Not a lot of people mess around with EAT hook validation or EAT validation. What the EAT can be used for is all those DLLs have a corresponding export table. They say, hey, I provide this functionality, and if you want to call it, this is where you have to call into in order to reach me. The advantage of hooking here is that device drivers, they always stay in memory. They're sitting around there at load time. Their EAT is set up properly. As new device drivers come in or other programs that want to call functions exported by the driver, they have to use this EAT. And that gives you a good place to hook in. An example of this would be Zone Alarm does EAT hooking. It actually is trying to patch a function in indis in the library it exports, which is called indis register protocol, in order to gain access to all the protocols such as TCP/IP that's available in the system. So kernel space is a great place to hook. IAT hooking isn't that interesting because that's usually a user mode technique that things like Hacker Defender and others have used in the past. However, kernel mode, the advantage of that is you have a single hook, and now you're globally jacked in to all the processes on the system. With IAT hooks, you have to get access to each individual process's address space. because they have a private address space. Therefore, if you try to hook kernel32.dll or ntdll.dll, you will only hook that process. However, once you're down at kernel mode, if you hook the system call table, etc., you hook every single process that may pass through that region of memory. Here's a diagram. Most of it showed up, I believe. So what we have here is a user mode program making a system call. That's how you request certain services of the operating system. Here we're doing a ZW create file. That will transition through the border in the center from user mode to kernel mode. In kernel mode, we're now in KI system service. KI system service handles all requests from user mode processes in order to request some functionality from the OS. It's going to look in EAX for an index into the system call table you see there. And at that index in the table is the actual address in the library NTOS kernel that's going to implement the functionality that the users requested. So in this case, it's nt create file. Here just shows you an example of what I said. The nt create file is not exported by NTOS kernel, but it resides in NTOS kernel.exe, and there is the pointer into NTOS kernel.exe. Typical rootkit subversion would be to hook into this table, modify that address to an address of its own, and then call the original function. And you might ask, why would you call the original if your whole idea was to bypass the original? Well, normally you still need the kernel to do the actions that the user requested, such as ZW query directory file would give you back all the files and so forth on a system. Well, you still need the kernel to do that for you, but when the result returns, you want the original to return to you. And then once you have the answers, you can then modify the answers before you pass them back up to user space. So an inline hook, you'll notice too at the bottom of all these slides, there's a URL for examples if we know of a good example. A lot of these come from rootkit.com where you can download and play with the example yourself. The source code is available to you. This one's called MIGBot. It does inline function patching. And with inline function patching, you're not hooking any existing table, such as the IAT or the EAT or the service descriptor table. What you're hooking instead is the actual binary in memory of the function. So in this case, you would patch some function in NTOS kernel with a jump into yourself. And then you'll see at the end, we'll call, the rootkit code would call the original function plus some offset. That offset was the amount of room we had to obliterate in the target function in order to insert our immediate jump. So another example of a hook is the ERP hooking. Every single device driver exposes a table of function pointers that will handle certain requests. Where these come into play is a normal process will say, hey, operating system, create me a socket, or create me a file, etc. However, that passes from the system call level through the system call table, and eventually hits an ERP. It's translated into an ERP, which is an IO request packet. That IO request packet is then chained to the specific device driver that handles that underlying resource, usually a hardware resource, such as the file system itself. So if you were making a call to perhaps write a file, that would eventually hit ntfs.sys, which is handling the file system for you. If you hook into that function table, you can intercept all requests for file IO or a lot of the networking IO type stuff. And there is an example in the book and also on rootkit.com. All the code from the book is on rootkit.com for free. And this is a ERP hook that I implemented that will hide all network ports by intercepting a single function to the device driver that's a query. And I can basically hide any port I want from netstat, etc. If you're doing a port scan, this isn't the method to use. Alexander may mention some ways that you can get past that type of detection. Interrupt hooking. Interrupts fire on also when the processes and other resources need the intervention of the kernel or the intervention of the underlying device driver that handles things like the network card and so forth. If you hook the IDT, you can gain execution control flow. And Shadow Walker was an example of this. It was a very advanced technique by Sherry Sparks, and also helped on that project. It was given last year, BlackHat. What that did is take over the page fault handler. If you hooked in the IDT, the 0E interrupt, you could handle all page faults. And we use that method to cloak code within the kernel. So if you're just scanning kernel memory, you have some kind of signature-based algorithm that you go look for rootkits in kernel memory. This rootkit would actually hide the presence of code so that your signature would no longer see it. Model-specific registers, they're the new IDT hooks of this decade, I suppose. This slide is specific to the Intel architecture. AMD has a similar naming convention. These are the IA32 sysenter is the one we're going to be interested here. There was actually a rootkit or Stoka that used this hook. In the MSR registers, you specify where certain things will be handled for you, such as a sysenter. A sysenter is a fast call, which you can transition quickly from user mode into kernel mode. Instead of going the old way, used to be fire off an int 2E, and now they use this faster sysenter call. If you change the registers, the MSR registers, you can register your own function to handle sysenter and so forth. And again, this was an example there of a current rootkit that's using this. And there is code on rootkit.com that'll show you how to do it. So process hiding circa 99 was the NT rootkit by Greg Hoagland. And it basically went to your system call table and patched up a bunch of functions. So that could hide registry keys, it could hide files, it could hide processes, and so forth. Then a few years later, I came around. I was working at an IDS company, and we were trying to detect some of these types of tricks. So instead of, I thought, well, looking at these tables and verifying that they're valid and so forth is a good way to go about detecting them. However, is there other types of attacks that could get around us? And I developed a proof of concept rootkit called FU that would go in and unlink the active process list so that you could take a process out of the active process list. It would still get scheduled. However, it wouldn't show up to task manager or any of the other processes.